Okay. So far what I have discussed is basically the Raoult's law, the non-ideal and ideal solutions, okay, and then azeotropic mixture. Today, what I will discuss is basically the solubility. Hmm, Okay. Now, when I say solubility, okay, that means what? That means, let's say A is my solute, okay, and B is my solvent. I'm assuming. So together, when I say A plus B, so they will form A dotted B kind of solution. Okay. So this is a thermodynamic process. Any like think like it as a chemical reaction. Also, two substance making a one substance. Chemical reaction or a thermodynamic process. So this will have a particular delta H associated with it, right? Enthalpy. Now this delta H is known as solvation enthalpy. Solvation, solvation enthalpy. Okay, solvation enthalpy. Now this solvation enthalpy we denote by delta H of sol. Now if I think that, let's say, two types of cases can happen here. Now when I say A is a solute, B is a solvent. Okay, so what I'm saying, so A is soluble in B. A is soluble in B. So what this suggests? So basically, in case of B, you have this kind of bond, not bond means, let's say, this kind of interactions, and in between this, you have, let's say, one space is there, one space. I'm assuming. Now, in this one space, your A can come and okay, A can come and sit. So a particular amount of A will come and will join in here. So what they will form? They will form a what means just a B A B, this kind of thing, a solvated thing. Okay, product. Okay, okay. Don't think about this. Don't think that it's a bond making. It's just a solvated part. Okay. Acha. So now let's say if you have excess amount of A, then what will happen? Then a few amount of A will accommodate it between two B. So the rest of the A will be remain in the solution by themselves. Now that kind of solutions is we know known as a saturated solution. Okay. Acha. So now when I say A is soluble on B, what that means? That means that this that actually depends on the nature of the B and obviously the nature of the A, and their nature definitely and has to be same. Let me tell you how. Because let's say if you have water as a solvent and if you have a sodium chloride as your solute, then sodium chloride is a polar, right? And water is also a polar, so there will be a polar-polar interaction. That's why sodium chloride is soluble in water. But instead of water, let's say if you have a benzene, what will happen? The benzene is basically a non-polar solvent, and in this non-polar solvent, the NaCl will not get solvated. Okay, so that's why the nature of the A and nature of the B is very much important. Okay, so nature. First point is nature. Okay, now let's say if I talk about this process, thermodynamic process. Okay, so in this case, thus if the reaction has to be proceed in this or this process has to be proceed in forward way, your delta H of solvation is has to be 0 greater than 0, right? Now, if you increase the temperature, what will happen? If you increase the temperature, since the delta H solvation is greater than 0, then your solubility will increase. And if I think the reverse, the delta H of solvation is less than 0. So in this case, if you increase the temperature, your solubility will decrease. So basically, this is nothing but the thermodynamic criteria. Okay, let's brush up just once. Spontaneity, delta G less than 0, delta S greater than 0, and delta H greater than 0. These are the condition of the spontaneity of any thermodynamic process. Okay, now this is the nature. Okay, so solubility, nature, and this is the reaction temperature dependent. Okay. Now, these things are applicable in case of the solid liquid solvation. Okay, and liquid liquid solvations also. But if I talk about, let's say, gas liquid solvation, okay, if I talk about a gas liquid solvation, so what is that kind of case? Okay, let's say I'm talking about a gas plus liquid solvation. What will happen in this case? Okay, think, let's say if you have a gas here container, and in this container you have a gas here and you have a liquid here. Now, since you have a gas here, this gas will definitely, what will do? They will exert a pressure on the liquid. Definitely. And one guy his name was Henry. You know what he said? He said that a gas will exert pressure is fine, and that pressure will be proportional to the mole fraction of the gas in the solution. That pressure, let's say P, giving here the pressure P, and this P is proportional to the X of, let's say, component G. I'm talking about the G. So this is in solution in here. This is in here. Okay, obviously, because if you increase the pressure, some more number of gas molecules will be solvated in the liquid and will make the solution, and in that solution the, let's say, the mole fraction of the gas is Xg. So P is definitely proportional to the Xg. Now, to remove the proportionality constant, what we can write is Kh multiplied by Xg, let's say. Now, what is the unit of this Kh? This unit of Kh is basically the unit of torr or atmosphere, anything, because it's basically, this is Xg is mole fraction, so this is unitless. So the unit of the Henry's constant, which is known as the Henry's constant, Hc, I will write here, the Henry's constant is unit of basically the pressure. Now, if I compare with the Raoult's law, Raoult's law, what he said that if you have a volatile substance, okay, more than one volatile substance, the volatile substance, the partial pressure of the volatile substance at the vapor pressure will be equal to the pressure of the ith component at PO state multiplied by xi, the mole fraction of that ith component in the liquid. Okay, so if I compare these two, this is also like same kind of. There he talked about the liquid which will vaporize and form a gas, okay, which is volatile and go to the forms the vapor and then is giving a pressure. But here what Henry said, the gas liquid mixture, okay, and gas is exerting the pressure. It is both are equivalent. You think? Okay, so if I compare, then this P0, which is the pure, is basically nothing but the Henry's constant, not equal, equivalent. I would say equivalent to the Henry's constant. Okay, and this is also we know as a constant quantity, and this unit is also torr slash atmosphere, and this unit is also torr slash atmosphere. Okay, so this is a significance of the Henry's law is basically nothing but the your uh what is that called? Nothing but the special case. Okay, special case. Okay, special case. Okay, and what kind of so Henry, what Henry said that we discussed already, and what are the applications you can find out? There are two major applications. Number one is carbonated water. Okay, the carbonated industry, when they make the carbonated water like soda or the cold drinks you drink. Okay, so that case, the pressure, that is basically the carbonate gas. Okay, and you have a liquid. So when you take out the cap, it pops up. Okay, so in that case, number one, the bicarbonate industry. Number two is that, let's say you who studies the marine biology. Okay, what they do, they calculate the amount of oxygen dissolved in the water. Okay, and this way, using this Henry's law, you can calculate. So this Henry's law has a wide range of applications. Okay, so this is fine. We discuss the solubility and the Henry's law and the gas liquid mixture. So next liquid lecture onward, what I will talk about is basically the qualitative properties. Okay, and finally, I think after this qualitative property, this liquid will this liquid then I will go to Van't factor and this chapter will end. Okay, so till then,